These solar heaters for heating houses cost $10,000 or $20,000, but this is their poor relative, which consists only of a layer of black paint and cheap polyethylene film. We understand that solar radiation will heat the black wall to 50 or 70 degrees Celsius, and therefore it heats the air which moves along this serpentine to this hole with a fan. This video will show how such a primitive thing can completely heat a house both day and night, and the entire solar heating system will have approximately the same construction cost as traditional heat pumps. But free solar radiation will result in savings of $500 annual on hot water and another $500 annual on home heating, because the electricity consumption will be 2 or 3 times less than in the case of traditional heat pumps. This is a more expensive relative, and it also heats a house when the sun is shining and the fan directs the cold air from the house along this pipe through this hole, and then the air moves as this finger shows. It is obvious that the air is heated by this hot black surface and goes out through this hole along this pipe into the house. This is another relative, and this insulation is important because it will resist heat leaks from this hot black surface. We understand that our type of solar heaters consists of one transparent surface and one black surface, unlike other types of solar air heaters, for example this type with pipes, and the power of this more expensive type is approximately this. At the same time, the power of our simple and cheap type is described something like this, and we see that here at high temperatures our cheap type produces several times less heat. But here, when the air temperature in other solar heaters is less than 30 degrees, our cheap type has good efficiency, and therefore let's use these features to heat the house in the following way. The area of our solar heater should be larger, and here we should install the second solar heater. These pipes are shown here, and they connect the solar heaters to the pit with 25 tons of gravel, which is surrounded by this thermal insulation. When the sun is shining, this fan creates this circulation of air, which is heated here, and then it heats the gravel to these temperatures. The gravel temperature will decrease when this second fan creates this circulation of air from the rooms, and it is obvious that this is the heating of this house at night and on non-sunny days, similar to this American house. These high temperatures of the gravel will be in November and March, but the winter months have such low temperatures which lead to an increase in the heat production by our solar heaters several times, and we could notice this phenomenon on this graph. Here we use a small heat pump, which sometimes heats the house, and it must take energy from the warm air, which is constantly heated by the gravel. In addition, the heat pump will sometimes operate in traditional mode, where it takes energy from the ambient air. That is why here we have to install two automatic dampers, which connect the heat pump either to this flow of warm air from the gravel or to this flow of cold ambient air, and below is a link to how one blogger makes a large damper. It would be better if the heat pump takes ambient air in the evening, when its efficiency is higher due to warmer weather. But the colder night air reduces the power of the heat pump, and therefore thermostat should switch it to warm gravel air. In addition, these short switches to warm gravel air remove ice from the heat pump, and now I am showing how traditional heat pump typically removes ice by wasting expensive electricity or heat. Very cold weather requires the use of this warm gravel air, which guarantees high power for our heat pump. Therefore, this gravel stores a reserve of heat for 3 non-sunny days in a row, if 25 tons of the gravel are cooled from these temperatures to this level. But in reality it will continue longer, because sometimes the heat pump will take energy from the ambient air, for example in the afternoon or during a warm evening. Of course, a long cloudy period will still take all the energy from the gravel, and therefore the heat pump will constantly operate on the ambient air. But usually cloudy weather is accompanied by warm nights, and therefore small heat pump will cope with the complete heating of the house. When a sunny day hits the top of the pit about 25 degrees, thermostats turn on this fan for heating the house without the heat pump. If this temperature is less than 30 degrees, the coolness in the rooms can turn on the heat pump, and therefore the heat pump and the fan can heat the house simultaneously. This is an option for the construction cost of the entire solar heating system at the level of $10,000, and these are expensive solar heaters, for example like this or like this. Now I will compare the cases of the location of the system in these two cities where the heating of the same house with an area of 100 square meters has these differences. We see that the location changes this savings on heating the house and this electricity consumption. These values are a consequence of the difference between this climate of sunnier Sofia and this climate of warmer Berlin, but with a longer heating season. Let's take a closer look at this case of the capital of Bulgaria, and these temperatures determine such heating needs of the house near Sofia. These are thermal kilowatt-hours from the heat pump in the traditional mode, using ambient air, and this is heating the house with the heat pump using the gravel air. This is heating the house with hot air from the gravel more than 30 degrees, without the heat pump. It is obvious that the sum of these kilowatt-hours is equal to this heat production from 90 square meters of our cheap solar heaters, and this is the number of sunny days according to that climate of Sofia. Here I took into account heat losses from the pit with gravel, and you can make sure that the sum of these kilowatt-hours for heating the house is equal to this heat consumption for each month, which means that the house is completely heated by our system, all 100%. Such small heat losses from the pit in December and January are not surprising due to the low temperature of the gravel in winter and this heat flow from the warmer groundwater. The heat losses were calculated based on these average gravel temperatures, and these temperatures were used to calculate this efficiency of the solar heaters and this electricity for the heat pump. We see that the sum of this electricity consumption by the heat pump is 2 or 3 times less than if all these kilowatt-hours were produced by traditional home heating with heat pumps. But we must also add this electricity consumption of all our fans for all 12 months of a year. This is one of the options for hot water supply, including in summer, and usually the gravel will heat the water of this steel tank to approximately 60 degrees, but Madison requires 70 degrees, which is guaranteed by this traditional electric heater.